Welcome back. When we left off last time, I had asked you to answer these questions on your own to test your knowledge. First question in section 2 here is, what are the 3 ways that machines make work easier? They multiply force, they can change the direction of the force, or they can increase the distance over which the force is applied. So they don't do one or the other of these things. Many times they can multiply force and change the direction of the force. So they're not independent. When you multiply force, you multiply the force by spreading the work out over a bigger distance. And this is a little different than number 3, where we increase the distance over which the work force is applied. This is kind of like using a rake or a broom, and you want to put in the force up at the top of the handle and have it come out down at the bottom of the handle. We're going to talk about that one some more as we go through the different machines. What is the trade-off for a machine multiplying your force, or what is the negative thing that happens? In order to multiply your force, you have to increase the distance over which the work is done. You get to use less force, but it's spread out over a longer distance. And we looked at 2 examples in the notes where the lady had to push stuff up a long incline plane in order to get the box lifted 1 meter. When she pushed it over 100 meters, she was able to use only 1 Newton force to lift a 100 Newton box. But the trade-off was that she had to push it up that ramp for such a long distance. Okay, if we increase the distance while using a machine, we'll get to use less force because there's a direct relationship between increased distance and how many times the machine will multiply your force. The 3 parts of a machine are the input or effort force. This is where the user puts in their force. The output force, resistance, or load force is the force produced by the machine. And then the resistance or the load is the object that resists being moved. And as we said, this relates to Newton's first law of motion, that objects at rest want to stay at rest, which is their inertia. And the work is going to be done on that object. Mechanical advantage is the number of times a machine multiplies your input or effort force. What's the difference between ideal and actual mechanical advantage? Okay, an ideal machine is a machine that would have no friction, and it would produce ideal mechanical advantage. An actual machine is one that we built, and it has friction. Friction is friction. It is produced. The actual mechanical advantage is the number of times the input force is multiplied after some input is lost to friction. Okay, simple machines. Now we're going to take a look at simple machines in general, and then we're going to go through each one of the 6 types of simple machines. So the definition of a simple machine is a machine that does work with only 1 movement. So it only has 1 or no moving parts. Okay? And so there's just 1 simple movement. That's why they're called simple machines. Okay? The simple machines make work easier 3 ways. Okay? First one is they can multiply our force. And the trade-off is having that long distance over which you have to do the work. You get to use less force, but you have to go a longer distance. And the machine then multiplies your force. Okay? It can change the direction of the force. It can increase the distance over which the force is applied, or it can do both of these. 3 parts of a machine. Okay? Is the input or effort force. This is the force applied to the machine by the operator. The output force or the resistance force is the machine applied by the machine to overcome the resistance due to gravity or friction. And then there's the resistance or load. That's the object that has its inertia and it has a resistance to being moved. Ideal mechanical advantage is the mechanical advantage of a machine without friction is usually calculated by the big number divided by the little number. Okay, so it's going to be the 2 parts of the machine where you put in the input or where you put in the output, and it's going to be the distance. So it'll be the 2 distances divided by each other. Okay, there's a short clip on simple machines that I want us to take a look at. And then there's a second one that breaks down the parts of the simple machines a little bit better. Okay, this is this little clip I wanted us to take a look at on the different machines and how work and force are related.
Hi, I'm Kirsten. Welcome to Real World Science. Every day, people use machines to get work done. Today, we're going to talk about a special group of machines called simple machines. What is a machine? When you look around, you'll see that people use machines every day. Some machines help people travel from one place to another. Some machines help people lift heavy objects. Some machines help people to cut, to drill, and to mix objects. A machine is any device that helps us to do work. Work is the result of a force moving an object. A machine helps us to do work. So, is this rake a machine? Sure is. It helps to do work. The rake moves the leaves. You wouldn't think it, but this baseball bat is a machine too. When you hit a baseball, the ball moves. That's work too. Work is done when a force moves an object. Every machine needs a force to make it work. Force is a push or a pull that changes the motion or shape of an object. It's force that produces movement. Force is also related to distance. If you change the force, you change the distance. For example, if someone lightly taps a ball using a little force, the ball will only move a short distance. But if you use a lot of force and hit the ball real hard, the ball will travel a longer distance. Scientists showed this relationship using a simple formula: work equals force times distance. We use machines to make work easier. In this program, we're going to concentrate on special kinds of machines called simple machines. A simple machine has a few or no moving parts, and there are 6 kinds of simple machines: inclined plane, wedge, screw, lever, pulley, and wheel and axle.
Okay, I want you to take a look at this little clip on simple machines.
Machines do many things. They help move dirt, lift things, and pump oil from the ground. Machines help skiers to get to the top of a mountain. And travelers to fly. There are also many machines that we may not think of as being machines. These are machines that we may use every day. They may seem too ordinary, too simple to be machines. But by understanding simple machines, you can understand much more about even the most complicated machines. We don't usually think of a playground as a place where work goes on. A playground is a place to have fun. But despite appearances, while these children are playing, many of them are also doing work. This kind of work is different than schoolwork, which involves thinking. In science, the definition of work is moving something over a distance. So this boy is doing work by moving his brother across the playground. Work like this requires force. The definition of force is any push or pull. Pulling a wagon involves force. Here's still another definition. Whatever is being pushed or pulled is called the resistance or load. Here, the boy being pulled in the wagon is the load. And here, the little girl being pushed on the swing by her mother is the load. Not only is there a lot of work going on, but this playground is also full of machines that help people do work. Machines on a playground? Well, in science, a machine is anything that helps people do work. Machines often help by reducing the force it takes to move something over a distance. So this seesaw is a machine because it helps these two boys lift each other up in the air. And this wagon is a machine because it reduces the amount of force it takes to move a younger brother across the playground. Machines like the seesaw and wagon may seem pretty far removed from complex machines like the ones shown here helping repair a road. But all machines are alike in that they help people do work. All machines are alike in another way, too. No matter how complicated some machines may look, all machines are made up of combinations of simple machines.
The first type of simple machine that we're going to talk about specifically is the lever. The lever is a bar that's free to pivot about a fixed point called a fulcrum. So the fulcrum is the fixed point that the machine pivots around. So like on a seesaw, it's the place where it's tilting up and down. So like this hand would be the fulcrum in this example. The effort arm is the part of the lever on which the effort force is applied. And it's the distance to where the effort force is to the fulcrum. The resistance arm is the part of the lever where the resistance force is applied. And it's the distance from the fulcrum to where the resistance force is the length of the effort arm. The ideal mechanical advantage of a lever is the length of the effort arm divided by the resistance arm or load arm. So there's a short clip I want you to take a look at on levers. In this little video clip, we're going to look specifically at the lever.
Lever. A lever is a simple machine. A lever is simply a rigid object or bar that pivots around a fixed point called a fulcrum. A lever reduces the amount of effort needed to lift or move an object. A good example of a lever is a seesaw. All levers have three parts. The first part is the object that is going to be moved, called the load. In this case, it's the kids on the seesaw. You also need a fulcrum. That's the fixed point where a lever turns. The third part of the lever is the effort. That is the effort or force you need to move the load. When you put force on the opposite end of the lever, the child or load moves. A lever is any bar that pivots around a fixed point or fulcrum. There are three kinds of levers. The first type of lever is called a third-class lever. A good example of a third-class lever is a rake. A third-class lever has the fulcrum at one end, load on the opposite end, and the force in the middle. The next type of lever is called a second-class lever. A good example of second-class lever is a wheelbarrow. On a second-class lever, the fulcrum is on one end, the effort is on the opposite end, and the load is in the middle. Another example of a second-class lever is a bottle opener. Here is the fulcrum on one end, the load is the bottle cap, and in the middle and the effort opposite the fulcrum. The third type of lever is called first-class lever. A seesaw is a great example of a first-class lever. On a first-class lever, the fulcrum is in the middle. The load is on one end, and the effort is on the opposite end. A hammer is another example of a first-class lever. Here's the fulcrum, the load is the nail, and the effort is applied to the opposite end of the bar.